bad word it is.
All right. Do you believe that there is a God? Never mind who or what you think God is. And I don't actually even need you to answer. This isn't I'm not trying to out you if you're an atheist or something like that, okay? So I'm not looking for anybody to raise their hand. But just in your own heart, do you believe that there is a God? Okay. If you do and you're willing to answer, what does it mean for whatever this God is to be God? What would make God God? I'll rephrase this slightly. I had a young man that I met. He was working at Whataburger, and we started talking. He asked me a very strange question. I never been asked this before. He goes, "So what do you think God's superpowers are?" I was like, really? It was so strange for me. But I think it kind of fits for this. What makes God God? Anyway.
All the way. All the way.
All-knowing, omniscient, okay? Do you believe that, by the way?
Yeah.
Okay. All right, cool. What else? If you have been here twice, you know I'm just going to wait you out.
He created heaven and earth.
Okay, created heaven and earth. Dr. Erickson today read from Genesis chapter 1. In the beginning, God created the heavens and the earth. At least this is the Christian and the Jewish belief, right? And for that matter, Muslim. Created man in his own image. Actually, it says create man in our own image. That's weird. Right? Be a plurality somehow. Trinitarian view. Okay. What else? What makes God God?
All powerful.
All powerful. Omnipotent. What else? What are some attributes or characteristics you think of God? And do you believe that? Somebody other than me, do you believe that God is all powerful? If you believe in a God, do you believe that God is all powerful? I think that's probably the number one thing that most people throughout the world believe about whatever God they believe in, is that whether that God could, whether that God does or doesn't, but that God could do anything. Could speak the world into existence, could change your life, could give you $1 million, could strike your child dead, could raise your child from death, could do anything. Like that's probably the essence in most people's views of being God. It wasn't always so. You look back, he was talking about these other civilizations. You look to the Greeks and the Romans, right? Did they have one God? No, they had a pantheon of God, tons of gods, right? And that's true of the Egyptians, it's true of the Assyrians, it's true of the Babylonians, it's true of all these cultures. In fact, the idea of monotheism, that there's only one God, that comes from the Jews. And you see it with Christians and you see it with Muslims, but you don't usually see it most other places. So here we are, we're at a Christian school. And so ostensibly, at least the school, and folks like me believe in one God, right? And can we know God? Yeah, what do you think? Is it possible to know God? And if so, how?
Spiritually.
Spiritually? Explain.
I mean, we don't know, like, I don't think you've met him. I don't think I've met him.
Okay.
But, I read the Bible. I know him spirit. I know him through the Bible. I know him through my spirit. I know I feel him.
Okay. So you think through so the Bible is one way that we can know God, right? What is the Bible?
Book of stories.
It's just a book of stories.
Not just a book. I mean,
Okay, well, that's what you said, but go ahead, tell me again.
It's a book of stories about Jesus and God.
Okay. Is it all stories? You familiar? Certainly there's lots of stories in the Bible, right? Genesis is full of stories. Exodus is one kind of big old story of how they got out of Egypt. Numbers is the story of them going through the wilderness. Ruth is the story of one little big group of women. First Samuel is the story of the anointing of King David. Second Samuel is the anointing of David becoming king. First Kings is the story primarily of Solomon, and then Second Kings is primarily the story of all these other kings. Stories everywhere, right? But First Peter's not a story. Right? That's a letter. Isaiah is not a story. It's filled with prophecy. But you said something really important. You said it's all about who?
Jesus and God.
Jesus and God. A lot of people might say that the Bible is God speaking to us. Like this idea that, and the Bible says this, that God dwells in light, and we cannot see Him. Jesus says no one has seen God at any time. So then if we can't see Him, and we can't talk to Him, how can we know Him? You know, do you know who's in the room next door? Do you know if there's anybody in the room next door? No, you can't see through that wall, right? Somebody with God or whoever would have to communicate with us. And that's what I certainly believe, is that the Bible is God communicating to us. It seems logical. If there is an entity outside of Earth, higher than us, that we wouldn't necessarily be able to understand or know anything about it. Think about this. If there was an ant crawling on this table, and you're up here, and maybe you're even talking, because can that ant know you? Can that ant really know much about you? I mean, you're on this whole other plane, this whole other level of magnitude. That's just an ant. What about a bacteria? Does a bacteria have any comprehension of you? No. Okay, so we have this idea that there's a God. We can't know this God on our own, but that maybe this God spoke to us through His Word. John chapter 1 says, in the beginning was the Word was with God, the Word was God. Then you go to verse 14, it says, and the Word became flesh, and He dwelt among us, and we beheld His glory. The glory is of the only begotten Son of the Father. So this idea that God spoke to us, even that all this is about Christ and about His Son. Why does this matter? It has nothing to do with chemistry, right? You're like, all right, I wish this guy would shut up now. Because in a minute I'm going to pray. And I haven't prayed for you guys yet, I don't think, have I? Maybe one time, I don't know. I need to start doing that. I'm going to connect all these pieces in just a moment, okay? I want to read something that I believe God wrote for us. So it's Psalm 127. So if you believe in this God, and you believe in this Bible, then God wrote this for you. Maybe not to you, but certainly for you. So it says this: unless the Lord builds the house, those who build it labor in vain. Unless the Lord watches over the city, the watchman stays awake in vain. It is in vain that you rise up early and go late to rest, eating the bread of anxious toil, for He gives to His beloved sleep. Read that one more time, okay? Unless the Lord builds the house, those who build it labor in vain. Unless the Lord watches over the city, the watchman stays awake in vain. It is in vain that you rise up early and that you go late to rest, eating the bread of anxious toil, for He gives to His beloved sleep. What is that telling you? What does that mean? What does vanity mean? Or something to be vain?
Pointless.
Pointless, worthless. So what's he saying is worthless?
Like, if you're not following God's path, then like what you're doing,
Okay.
maybe pointless.
Specifically here he says, unless the Lord builds the house, the laborers build in vain. Unless the Lord keeps the watch, the watchman watches in vain. Like if the Lord's not in it, you're wasting your time. I actually built homes or did home remodeling for a number of years, and I can tell you I had days, I had to cut one little piece of tile, and I'd cut that tile and it'd break, 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 and about the fifth, sixth time I'm ready to give up, and finally I go, Lord, I need you to help me cut this tile. And then the next time it works. I've had that in studying. I remember taking organic chemistry, And man, my life was falling apart around me. I was taking like 26 credit hours and working full time and coaching, and personal relationships were a train wreck. And at first I just couldn't sleep because I couldn't sleep, but then I couldn't sleep because I had anxiety, and my life is just falling apart. And I'm trying to read stupid organic chemistry because I have to pass this class, and I'm reading the book and reading the book and reading the book. I'd read it 4 or 5 times, and I'd come away and it was like I hadn't read a thing. It was like it was in Portuguese or something. I mean, I did not understand a word I was reading. It's like, okay, Lord, I need you to help me. How often, maybe, if you believe in this God, do you believe that you've done a lot of things in vain and you didn't seek Him to help you? And I feel like that right now in my life. I got a lot going on, man. I'm working here full time. I'm pastoring a church full time. I got my 4 kids plus another 4 kids in my house that we're helping with and all. It's like, if the Lord does not teach this class, I'm in trouble. If the Lord does not prepare for this class, I'm in trouble. And I wonder for you, if the Lord doesn't help me with this math, I might be in trouble. If the Lord doesn't help me learn this material, I might be in trouble. So I'm going to pray for us, and then we're going to get started, okay? Heavenly Father, we thank you for your word, and we just thank you that you tell us things like this that point us to the vanity of our life, and just trying as hard as we can, that we need you, Lord. Pray that you would help us, help me to teach clearly and concisely, making connections with everyone here so that these things stick, that they will do well. I pray that you'd help them to understand the content and to think about what they're learning and to ask good questions when they need to, and to be diligent in their studies and for those things to pay off. We all have just so many constraints on our time. Lord, I just pray that perhaps some things I said today and read for your word, they don't seem so true to us. I just ask that you would. Ask that you'd reveal yourself throughout the course of this semester. That you'd use this school and this class in our lives. We pray this in Jesus' name. Amen. All right. Let's do just a little bit more review, okay, before we move on. Because if we don't get this now, we're going to be in trouble forever in this class. So here's what I want you to do. Do a little bit together here. Let's see if I can't put this up there, and that will help us a little more. All right. So you got it on here, you got it up there also. If I had 1 kilometer, right? 1 kilometer is equivalent to, and I know that we haven't done hectometers or hecto yet because we don't really use that one so much. But we've done deca, and we've done meters, and we've done deci and centi and all that kind of stuff. But 1 kilometer is equivalent to how many centimeters? You just count it out, right? 100,000, right? Y'all see that, right? How many meters is it equivalent to? 1,000. How many millimeters? Oh, I didn't get enough zeros in for the millimeters. Y'all add a 0 to that. I messed that up. 1,000,000. Okay. And I've got it there also in scientific notation, right? So 1 in scientific notation is 1 times 10 to the 0 power. 10 to the 0 power is just 1. So it's kind of like an identity property. 1 times 1 is 1. 1 kilometer is 10 hectometers, and that's 1 times 10 to the first, which is just saying 1 times 10. Right? So that whole thing is just pretty linear, pretty straightforward. You can see it there for, I've got another one going where I started with the next column over. I started with 1 millimeter down there at the bottom, right? Well, a millimeter is how much smaller than a centimeter? 10. So if I have 1 millimeter, it's 0.1 centimeters. And it's 100 times smaller than a decimeter, right? So it's 0.01 decimeters. It's 1,000 times smaller than a meter, so it's 0.001. And of course, you've got the scientific notation there. Do me a favor, right now, just look at the first two sets there, okay? Where I filled out everything on. And I want you to tell me if you have any questions about what you see. Does any of that not make sense? You feel good? 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 Don't feel good? All right, good. I went one more column over, and I started with just 1 meter, right? So 1 meter is how many kilometers? 0.001, right? We could say this in 1/1000 is how you just said it. That's great. How many meters would it take to have a kilometer? 1,000. How many meters are in? How many millimeters are in a meter? 1,000. And of course, we have those expressed in scientific notation, right? Let's go to this fourth column over. I gave you 2 numbers, right? We have it in decameters. I have 2.4 decameters. Written in scientific notation, it's just 2.4, right? Times 10 to the 0 power, right? Okay, how many meters is this? How many meters in a decameter? Yeah, how many meters are in that decameter? No. 10. Right? Each gap here is 10. It's a base 10 system, right? So 1 decameter equals 10 meters. I have 2.4 decameters, so I need to multiply by 10, and I get 24. So I got 24 meters, right? Well, how many decimeters is that going to be? I'm going to multiply this by 10, or I can multiply that times 100. Either way you want to look at it. But that's going to give me how many? What number? 240. Okay. And if I were to go to centimeters, it's going to be 2,400. And if I want to go to millimeters, 24,000. Good. Okay. And if I want to go up, I want to go to hectometers. So my 2.4, am I going to get bigger or smaller? Smaller by a factor of, say, 10. 10. So my 2.4 becomes 0.24. And if I want to go to kilometers, 0.024. Good. So far, so good. Okay, so then our next step would be, let's put this all in scientific notation. What should I have at the beginning of all of these? I should have 2.4 at the front of all of these. I will hook you up in just a moment. 2.4 times 10 to the something, right? And then the something just changes. So do me a favor, fill that out, okay? While I try to find it. Well, if you need it, here's this. If you don't, give it back to me. Y'all working on this? Good. Get something like that. Okay. Let's do another column. Let's go to the bottom. Let's go to the bottom left. So I have it in scientific notation. I'm going to write my units up here, okay? So I'm going to do kilometers, hectometers, decimeters, decameters, meters, decimeters, centimeters, and millimeters. And I have 2.7 times 10 to the negative 1 centimeters. Okay. How many centimeters is that? 0.27, he says. 10 to the negative 1 tells me I do what with this decimal place? Move it over to the left one time, right? So I get 0.27. Good. Well, if I have 0.27 millimeters, or centimeters, how many millimeters will I have? 2.7. I got to multiply it by 10, right? How many decimeters will I have? 0.0027. Y'all are getting it. And then the next one? 0.0027. Now I can just keep going up, right? I mean, I don't even have to think at this point, do I? And that's cumbersome to write, right? You don't want to deal with that. I mean, how easy would it be to put that into a calculator wrong? So we do the scientific notation thing. You'll feel good? Well, I'll give you a minute, sorry.
Do we write in the scientific notation?
Yeah, so we're going to start. So 2.7 times 10 to the negative 1 centimeters, what is that in millimeters?
2.7 times 10 to the 0.
Still, all these are going to have 2.7, right? Times 10 to the something. If this was negative 1, this... Huh? I don't know, I couldn't hear you.
What is that measure?
So this is the one that I gave you, right? It's there on it. So if I have 10 to the negative, 2.7 times 10 to the negative 1 centimeters, how many millimeters will that be? I've got to multiply by 10, right? So this negative 1 becomes 0. Good. Okay? And then this, all these will be 2.7 times 10, right? If this is negative 1, what's that? Negative 2, negative 3, negative 4, negative 5, negative 6. You don't want any more. You're bored, you're done, you're ready to roll. Sylvia's ready to go. Ingrid, is that a yes? Do one more? We're good. Okay. Awesome. Okay. Well then. That pretty much covers chapter 1. I ask this again. Have you all logged into Moodle?
I finally got in.
Okay. Ingrid, you log into Moodle?
Yes.
I'm sure you guys have not.
Yeah, I did
Okay.
that.
Okay, cool. So your textbook is there. It's just going to say textbook and like a link, and you just click on it. It's free. You download it. We've completed chapter 1. There's a practice quiz up there over this stuff. I've got to get another practice quiz up over some of the vocabulary. Unfortunately, the first lesson where I did all that vocabulary did not record, so you're basically going to need to go back and read the book. Okay. I do have like a set of notes because that book has like 200 vocabulary words or something in the first chapter. You don't need all that. You don't need all that. So I've listed out for you the ones you do need to know. Okay. And I'll get a quiz up for it also. It's a homework quiz, so homework counts for like 10% of your grade. I'm not overly worried about it. That's there for you, not for me. It's for you to know how you're doing in the class or whether or not you understand the stuff. The things I put up on Moodle are the things that it's going to be what you're going to need to know for a test. Okay. All right. So if you had gone to Moodle today, you've probably found all kinds of new stuff up. I was busy last night. Okay. There's some more practice for some of this, dimensional analysis and things like that. These are just like little, here, I'll just click on it real quick, okay? Oh, that's not the one. is that one? So it's like a little applet thing that you can go and do and practice, and it'll tell you how you're doing. And you'll know. And if you feel great with it, then skip that. If you need more practice, then it's there for you, okay? Be ready for notes. Here we go. I can talk to you about all these things and all these experiments. Today we're basically looking at the structure of an atom and what's in it and how do we know and how did we discover it. The history of a lot of this is really cool. I'm not going to bother you too much about Democritus and all this. I mean, the history of that's fine. It's Greek. It's a little boring. But when we start doing experiments, it gets really cool really fast. So, you ready? Here we go. Where did Thomson go? Okay. Let's do this.
A cathode ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the two metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes this specially coated surface, the cathode ray produces a strong fluorescence or bright light. When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate-bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles.
Stop there for a second, okay? So this guy, Thomson, came up with an experiment. He found a source of what ultimately we know as electrons. It didn't have a name yet when he started doing this. But he found a source of them. He did some experiments on them, okay? And so he set up what we call a cathode ray tube. They call these, that's what they call this thing. These used to basically be in like TVs and stuff like that. So he's got a source over here. And he shoots it through. This thing's in a vacuum. There's, in a vacuum or a near vacuum, in a perfect vacuum, there's no matter in there. There's no mass. So there's nothing to interfere with this. And then it hits this receptor over here. And he found that whenever it hit, it phosphoresced, okay? So he could see that it was hitting. It would glow for a moment, all right? Great, who cares? And he kind of made this little... So this is a negative charge, and this is a positive charge. And so that matters. These things are firing straight through, okay? So far, okay, who cares? But then when he starts doing this and he starts adding plates to it with charge. So he's got something with a positive charge, and I think on that example, the positive was on the bottom and the negative was on the top. Well, what happens to like charges? They repel, and opposite charges they attract. So what he found was that this thing was attracted here. And so it changed course. So that just told him this thing must have a negative charge. It has to. And obviously if you put this near it, if you like lower this to it, what's it going to do? It's going to repel. And if you flip them, it should do the same. Let's go ahead and take a look at that.
We know these negatively charged particles as electrons. A moving charged body behaves like a tiny magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction. In 1897, J.J. Thomson, an English physicist, determined the charge-to-mass ratio of an electron. He adjusted the electric field so that the electrostatic deflection, theta E, was the same as the magnetic deflection, theta B, and was able...
You do not need to know this formula. Okay? This is over anything we're worried about.
To calculate the charge-to-mass ratio of an electron using the following equation. where E is the applied electric field, theta is the angle of deflection, B is the applied magnetic field, and L is the distance traveled by the cathode rays. Thomson determined the charge-to-mass ratio of an electron to be negative 1.76 times 10 to the 8th coulombs per gram.
Okay. So he took a given mass of electrons, and so he knew the grams, right? And he shot them through, and based on what he was doing, how he was manipulating the fields, he was able to determine the charge, right? So I wish I had written that number down. Let me go back real quick.
A cathode ray tube is the forerunner of...
So he was able to come up with negative 1.76 times 10 to the 8th coulombs per gram. That's charge of an electron, or charge of electrons per unit mass. You don't actually need to know this, okay? If in certain circumstances maybe we would, but for what we're doing, you don't need to know this. You just need to know that this exists. So one of the most important things that was discovered about matter at this stage of the game is that not everything is made up of the same stuff. A couple theories of matter before this was that everything was made of a combination of either earth, wind, fire, or water. That's the Greek view. Or there's a classic view that just it's made up of discrete things called atoms, but the atoms are just like solid little balls, and they're just solid, and that's all there is to it. But this shows that there's something smaller, and it's got charge, and that's important. This will become to be known as an electron, right? Just hold on to that thought. All these pieces are going to come together here. Pull the next one. So then let's go to this next one, the Millikan oil drop experiment.
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron.
Stop there. The first guy was able to calculate that in any given unit of mass, this, for 1 gram, then I'll have negative 1.76 times 10 to the negative 8 coulombs per gram. It's a constant. Over and over and over again, he found this experimentally. This guy comes along and he starts doing weird stuff. Who would even think to do this? He's doing, I'm going to take oil droplets, I'm going to ionize them, I'm going to try to magnetize them and get them to just hover. That's cool. I'd be all about that. But I don't know that I could think to do it. So one of the things that you saw there was he determined mass by terminal velocity, right? So gravity, the force of gravity accelerates things at a constant rate of acceleration, 9.8 meters per second squared. So he can just determine, he knows where they're falling from, where they're falling to, how far they fall. He's able to determine how big each droplet was. Then he was able to, so he knew, okay, I've got this unit, I've got this many grams. Then he looked at charging them, and he was able to calculate the charge on them, and not all of them were the same size, but no matter what size they were, they had some multiple of this much charge. And what was happening there is each drop might pick up 1 extra electron, 2 extra electrons, 10 extra electrons, and so it would be a consistent multiple of this. I'm sorry, that's the gravity, or the mass. He was able to come up with the multiple of the charge there. And then doing that last experiment, he was able to determine the mass. So this guy, Millikan, determined the mass and the charge of an electron. First guy realized there's a fixed ratio. Second guy actually calculated it. The mass, this mass is crazy tiny, right? So the mass, for right now, write this down. I'm never going to make you memorize this, okay? If you ever need this, I'm going to give it to you. You don't need this in your life. So the mass of an electron is 9.10 times 10 to the negative 28 grams. And aren't you glad for sign notation? That'd be a lot of zeros. That joker is small. The charge of an electron so this here is 1.60 times 10 to the negative 19th coulombs. That's not a unit measurement that you use all the time. I'm going to hit play real quick, just to finish it up.
The mass of an electron, 9.10 times 10 to the negative 28 grams, is an exceedingly small mass.
I guess that's it. Okay. So now, let's go to the next one. Let's go to Rutherford.
It's 2024, and you're still using the same cable network?
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the centre of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter, we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We replicated that with modern detector technology. In its current position behind the foil, it will measure 1 count every few seconds. As Rutherford deduced, most of the gold atom is empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, what we're doing here, is taking a beam of particles, firing them at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In this case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behavior of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometers in circumference. What was happening was that the alpha particles were going through and missing the nucleus, because the nucleus is extremely small, and the atom, by comparison, is very big. So it's almost all empty space. And we had to wait a long time before one of those alpha particles hit the nucleus almost head on and bounce back into our detector.
Let's talk about Rutherford's experiment. So our guy, Rutherford, he's playing around with radioactive material. Very dangerous. They're testing things. He has a source of what we call alpha particles, okay? Alpha particles are huge, when we talk about radiation, right? You're familiar with that word. There are 3 primary types of radiation that we'll talk about. We'll talk about alpha particles, which are huge, beta particles, which are tiny, and we'll talk about gamma rays, which are light, and so they have no mass whatsoever, but they're crazy high energy. So alpha particles, they're usually expressed like this, the Greek letter alpha. It's basically a helium nucleus. Okay, so in helium you have 2 protons and 2 neutrons. The charge on a neutron, it's like the name, what is it? It's neutral. The charge on a proton is positive. So this thing has a +2 charge. It's very, very positively charged, right? That matters for what we're going to look at here. He's got a source, okay? And he's shooting out helium nuclei. Just rapid, these things are just flying out of there, right? And this is commonly called the gold foil experiment, because like you see here, he literally just this like paper thin, the thinnest piece of gold foil you can imagine. He sets up right here, okay? And he sets up, the other thing he sets up here is like a phosphorescent field, okay? Kind of like in the last one. And when this field gets hit, it glows. They literally did this experiment in the dark. Like he and a bunch of grad assistants just sitting there counting little blips of light. Because it phosphoresces, but it's not crazy bright. It's not like a neon light. So they're doing it in the dark. Just imagine just sitting there for hours counting. So most of these just shot through. They got blips like crazy right here. I mean, that one went nuts. Well, how does an alpha particle shoot through a piece of gold? Like, you can't put your finger through a piece of gold. You can't see through a piece of gold. The only way you can get through is if there's empty space. And there was a lot of empty space in a piece of gold foil or in a gold ring or in your chair, even in your brain. Like, it's almost all empty space. So almost all of this passed through. But it didn't all pass through. Okay? Some of it went here or here. Some of it went like here or here. The ones that went here, it's because or at least his deduction was, that it got close enough to the nucleus, something positively charged in the nucleus, that reaction caused it to deflect and go off at an angle. And his deduction here was that it actually hit and crashed backwards. These didn't happen very often. This happened all the time. So he was able to deduce that it's mostly empty space, but that there's something positively charged there in the center, and that whatever's going on in the atom, part of it is positive, and it's separate from whatever's happening that's negative. They knew there was positive stuff, they knew there was negative stuff, but previously it would have been like, overall that the atom's got to be neutral. It's protons and electrons kind of just jumbled up, but then you wouldn't get this result. You only get this if you've got like a solid, positive kind of a core thing going on, okay? So, Rutherford figures out for us that in the center of the atom is a positive charge separated from the negative charge. Let's go to the next one. Let's do Chadwick. Let's see, I think it's 727 or something like that. Yeah. So if you, like I made a little note on this one, it says start watching at 7:27. You don't need the whole Chadwick video. You can, I mean, it won't hurt you, but the part I want you to see starts at 7:20.
Nuclei. They were usually about double the mass of all the protons put together. Was there another particle in the nucleus? In 1932, James Chadwick, a student of Rutherford's, discovered a beam of new particles with about the same mass as protons. He did this by shooting alpha particles into beryllium atoms and knocking these particles out of the beryllium nuclei. The beryllium target was much thicker than Rutherford's gold foil, so there were many more nuclei for the alpha particles to make direct hits with. Beryllium's nuclei has an atomic number of 4, so he knew that they had 4 protons each, but he was experimenting to find a new particle in the nucleus. When these particles were struck by the alpha particle bullets, they were knocked out of the nucleus and then continued in a beam that Chadwick could study. This beam did not bend when passed through charged parallel plates, like the electrons of Thomson's experiment did. Remember, it was the electron's negative charge that made them bend when going through the plates. This meant that the newly discovered particles had no charge. Because these particles were electrically neutral, he named them neutrons. Chadwick had an eventful life. During World War I, he was a prisoner of war in...
Fascinating, but you don't need to know that. Okay. We've got electrons. What are other 2 subatomic particles?
Neutrons.
Neutrons and protons, right? Masses and the charges of protons and of neutrons. What's the charge on a proton, positive or negative? It's positive. gonna look an awful lot like this, okay? Except, I'm sorry, like this one. But instead of being negative, that should have a negative sign there. Instead of being negative, it's gonna be positive. All right, so,
That's the wrong one.
huh?
You rolled for neutron.
Thank you. The mass of a proton, I'm going to write as 1 AMU.
Atomic mass unit.
Atomic mass unit. That's the average mass of a carbon atom divided by the number of unit or of molecules in there. So, or subatomic molecules in there. The mass of a neutron is also going to be basically 1 AMU. And the charge is going to be 0. For all intents and purposes, I could have probably simplified this. If you ever need this, I'm going to give it to you. If you ever need this, I'm going to give it to you. I'm going to give you this very simple one, okay? We're going to do protons, we're going to do neutrons, we're going to do electrons, okay? Charge on a proton is positive. Charge on a neutron is neutral, right? There is none. Charge on an electron is negative. The mass on a proton is 1. Charge on a neutron is, I'm sorry, not charge, the mass is 1 AMU. The mass on a neutron is 1 AMU. Mass on an electron, for all intents and purposes, is 0. Okay, we're rounding here, obviously, right? So this is our symbol. This is our charge. This is our mass in AMU, atomic mass units, roughly the size or the mass of a proton, okay? The only other thing that we want to consider is location. I'll show you another video here in a second, okay? Is it really that late in this class?
It is 1:27.
That's crazy. I feel like I just started.
Yeah, doing something
Should be. What is going on?
maybe the video no longer exists.
I just did it last night. Try a different. What?
Okay, I think it's just something wrong with Google.
Oh, by all means, let me try a different browser. It doesn't link. All right, here's what you need to know then, since this is not going to cooperate. I really want you to have that. You need to see that video. It puts all these pieces together. You need it. Give me 1 second. Let's see, maybe I'll do my history or something. Last night. And I don't know.
I have no idea what's going on with that.
Rutherford atomic model, Rutherford cold oil.
That was not it. Here it is.
When you think of the word basketball, the first thing to mind, an orange sphere, probably, or perhaps your favorite athlete driving home a slam dunk. Now, do you know what's inside a basketball? Have you ever seen the inside of one? Well, even if you've never seen the inside of a basketball, you may have a general idea about what you would find. The same thing is true for atoms. Generations ago, people didn't know exactly what was inside an atom, but they had some ideas. Around 400 BC, a Greek philosopher named Democritus came up with a theory that everything in the world was made of tiny, indestructible particles called atomos, which means uncuttable. He believed that the properties of materials depended on the type of atomos they were composed of. For example, sour or sharp-tasting things were made of particles with pointy edges. Sweet stuff was made of more rounded or smooth atoms, and metals were composed of hard atomos. Apart from this shape misinterpretation, he was basically on the right track about atomic composition, dictating the properties of a substance. However, this theory was largely discredited by Aristotle, the original social influencer, who believed that everything on this planet was made of 4 elements: earth, fire, water, and air. The next step in atomic theory development didn't happen for nearly 2,000 years, when British chemist and meteorology enthusiast John Dalton raised some interesting questions. He conducted experiments where he mixed 2 gases and observed their behavior. He noticed something rather curious when nitric oxide was allowed to interact with atmospheric oxygen. 36 measures of pure nitric oxide reacted with 100 measures of air to create 80 measures of a new gas that was neither nitrous nor oxygenous. This intrigued him quite a bit, so he conducted the same experiment with different volumes of gas. He observed that the gases reacted with each other, but only in a fixed ratio. This gave rise to the law of multiple proportions and the theory of atomism. Following his breakthrough, Dalton proposed that everything in the world was made up of atoms, tiny, indestructible solid spheres that were unique for every element. Atoms of different elements combine to form different compounds and are rearranged during chemical reactions. More than 2 centuries of scientific development have passed since he first proposed that idea, but some aspects of that model remain uncontested to this day. Until the late 19th century, atoms were envisioned as indivisible particles, but that belief was shaken by an English physicist named J.J. Thomson and his trusty cathode ray tube. Inside a nearly vacuum glass tube, a visible beam of particles, or cathode rays, was generated by applying high voltage across metal electrodes. The stream of particles produced from the metal deflected away from the negative charge and directed towards the positive charge. After repeating this experiment several times with other metals, he came up with the first atomic model, the famous plum pudding model. This model characterizes an atom as a particle that is composed of a positively charged mass, the pudding, as well as tiny negative charges embedded in it, like plums. After some initial resistance, this model became quite popular in the scientific world. Even so, New Zealand-born Ernest Rutherford was not convinced. It was the early 1900s, radioactivity was all the rage, and during his work on radioactive decay, Rutherford discovered alpha, beta, and gamma rays. He wanted to develop a method to detect alpha particles and use it to probe into the structure of an atom. He did what every physicist at the time did. He came up with an experiment. The gold foil experiment, also known as Geiger-Marsden experiments, consisted of a thin sheet of gold foil with a circular zinc sulfide-coated screen behind it. The screen would flash every time an alpha particle hit it. Rutherford expected the particles to bullet through the foil and hit the screen behind it, and while most of the particles did behave as expected, some were deflected at an angle greater than 90 degrees. Backed by his observations, he came up with a new atomic model that disproved the previous one. He proposed an atomic structure where most of the atom's mass was concentrated in a positively charged center, which he later named the nucleus, around which the electrons orbited like planets around the sun. A year after the publication of Rutherford's atomic theory, Niels Bohr found a discrepancy in the model. If electrons were orbiting around a positively charged center, at some point those electrons would lose their energy and collapse into the nucleus, thus making the atoms unstable. However, that wasn't the case, as atoms were generally quite stable, aside from the radioactive ones. This is where quantum physics comes into the picture. He used the concept of quantized energy to propose that electrons moved around the nucleus in fixed orbits or shells. A shell closer to the nucleus has lower energy, while the one farthest away has the highest energy. If an electron jumps to a lower energy orbit, it would give out the extra energy in the form of radiation, thereby maintaining atomic stability. Even though Bohr's model doesn't hold true for complex, multi-electron systems, this model is still the most popular representation of atomic structure in most
It's the one we will work with.
No matter how much we try, there is no avoiding the complexities of quantum mechanics. With the establishment of the quantum behavior of entities like electrons, it became quite clear that Bohr's atomic model didn't satisfy the Heisenberg uncertainty principle. According to this principle, it's impossible to know the exact position and trajectory of electrons in an atom, which means they can't exist in fixed orbits, as Bohr hypothesized. Combining the concept of wave-particle duality and the uncertainty principle, Erwin Schrödinger came up with a quantum mechanical model of an atom. In this model, the electrons did not revolve around the nucleus in circular orbits, but rather as electron clouds in an atomic orbital, a region inside the atom where the probability of finding an electron is the highest. He also formulated the Schrödinger wave equations, which would help us accurately calculate the energy levels of electrons in an atom. This new and improved atomic model does not tell us where an electron is, but where it could be. Clearly, our understanding of what's inside an atom has evolved remarkably over the last few centuries, but it was only possible because having just a general idea about atomic structure simply wasn't good enough for some people. They dug deeper, often dedicating their careers and lives to the pursuit. And now we know so much more about the stuff that makes up our planet.
Ooh. Got 13 minutes. Let's go. So that was the one there that's of particular interest for us right now is the Bohr model, okay? I don't even necessarily care that you know the name of where it came from, but this is what we're going to be working with. So in the Bohr model, you have a nucleus, okay? Characteristics of the nucleus are that it's going to have a positive charge, right? And it's going to consist of two subatomic particles. They're going to be protons, and they're going to be neutrons, right? Okay? So we're going to have protons and neutrons in a nucleus. And then we're going to have electrons in shells or orbitals, okay? And so the thing about these shells or these orbitals are that they're at different distances from the nucleus. There are reasons for this. Again, this is a model. It's not perfect, but it's not bad either. So here's the thing you need to know. This first shell or orbital can only have 2 electrons in it, okay? And that is it. If I try to put a third electron in that tight of a space, it's going to get repelled out because of light charge. It cannot be there. And so it's got to go to the next orbital or the next shell. That next one can hold up to 8 electrons. Scam likely. Find it scam, no. Okay. Right? We're going to pause here. We're not going to go past this right now. We will, but we're not going to go past it certainly for today. Okay? So right now, what we want to concentrate on is 2 electrons in the first orbital and 8 electrons in the second orbital. Okay? So next thing we want to talk about is atomic mass and atomic number. Okay? Let's do atomic number first. You know how I determine the atomic number?
How many protons it has?
How many protons it has? Hydrogen, how many protons does it have?
1.
1. Helium, how many protons does it have?
2.
2. Lithium, how many does it have?
3.
3. Boron, or excuse me, beryllium.
4.
4. Boron.
5.
5. Carbon. Nitrogen.
7.
Oxygen. Fluorine.
9.
Neon.
10.
10. Okay, so I handed you a periodic table. Where am I going to find the atomic number at on a periodic table? It's in the upper left, right? So let's do right here, let's go like this. Here's a box. My atomic number, I'm going to do hydrogen here, right? So that's going to be my atomic number. And my symbol is going to be here. We assign each element a symbol. And then generally I'll write my atomic mass down below here. This is 1.01. That's going to be my atomic mass.
And that's just an average.
That's an average atomic mass, yes. We'll get to that coming up. So my atomic number is the number of protons. My atomic mass is different though. Take a look at carbon. What's carbon's atomic number?
6.
6. What's its atomic mass? 12. What's oxygen's atomic number?
8.
8. What's its atomic mass?
16.
16. How about helium? What's its atomic number?
2.
2. What's its atomic mass?
4.
4. Krypton on the far right, number 36. Atomic number? 36. Atomic mass? 83.6. There's a difference between atomic number and atomic mass, right? What's in my atomic mass? Which 2 things on this chart have mass? Protons and neutrons, right? So atomic mass equals protons plus neutrons. Okay? You need to know that. Here's what I want to know. I'm going to give you something, okay? I have an element that has 5 protons and 2 neutrons. I want to know the atomic mass and I want to know the atomic number. You shouldn't have to think about the atomic number. What is it?
5.
5. What's the atomic mass?
7.
7. How do I get that?
And
My atomic mass is protons plus neutrons. So that's 7. My atomic number is always going to be my number of protons, okay? Let's do this differently. I've got, my number of protons is 17, and my atomic mass is 22. How many, what's my atomic number?
17.
No. Oh yes, I'm sorry, I thought I wrote 7. Yes, it's 17. right? Because my number of protons equals my atomic number. What is my number of neutrons? 5, because protons plus neutrons equals 17. Let me write this in a little trickier way. A neutral atom, okay, so no charge overall in the atom, right, has 14 electrons and has a mass of 24. How many protons does it have?
14.
Should have 14, right? I have 14 negative charges. I should have 14 positive charges. If my atomic number is 14 and my atomic mass is 24, how many neutrons do I have?
10.
10. And what element is this?
Silicon.
Silicon. Okay. Let's try another. I have an ion. Do you know what an ion is?
Yes. It has a charge.
It has a charge, okay? So this is a +1 ion. What does that mean for me? Do I have more or less electrons than normal?
Less.
I have less electrons than I normally should. I have less electrons than I have protons, right? How many less?
1.
1 less. Good, okay. I have a +1 ion that has 5 electrons. So I want to know, first of all, what is its atomic number?
6.
6. What element is this?
Carbon.
It's going to be carbon. And it has a mass, actually it has 3 neutrons, so I want to know its mass. 9, right? Because this meant that I had 6 protons plus 3 neutrons gives me a mass of 9. So far so good? Y'all are doing great with this. This is awesome. How am I doing on time? Okay, let's see what else I want to get to today if I have a chance. Yeah, let's talk about isotopes, okay? You know that term? You heard that term before? Okay, so it's isotopes. Let's give a simple definition for this. Iso means same, okay? They're the same, but they're different. Something's the same about them, but something's different about them. They have the same what? Atomic number. So these are atoms. Let's see if this will work. Atoms of the same atomic number. But a different what?
Atomic mass.
Atomic mass. If I have the same atomic number, then I know I have the same number of what? Subatomic particles? Protons. But if I have a different atomic mass, I must have a different number of neutrons. That's worth knowing. I mean, I don't know if you need to write it down. If you know it, you know it. But if you don't, then write it down. So they're going to have the same number of protons, but a different number of neutrons. Okay? Significant. Quite significant. We'll start with the simplest one of all. I want you to draw this for me, okay? I want you to draw and I want you to draw this. Draw that for me, okay? Give me a Bohr model of that. The Bohr model is going to start with the nucleus, right? So what's in the nucleus of each one? And then of course we're going to put in any electrons that we need. If I'm doing this, I'm going to do a nucleus here. I like to just put a positive charge for my protons. I know that this has how many protons?
1.
1. It comes from my atomic number. This one is going to have how many protons?
1.
1. It comes from my atomic number. This one, does it have any neutrons? No, because my atomic mass minus my atomic number here is 0, so I have no neutrons. But here I have 2 for an atomic mass and 1 for an atomic number. I subtract the number from the mass and I get 1 neutron. So I'm going to put a neutron, a symbol for a neutron in there, okay? And this one has how many electrons should it have if it's neutral? It should have 1, right? And you can do it like this, or you can do it with dots, or there's all kinds of ways you can go about this. We'll do the same thing here, right? So this is a atomic mass 1 hydrogen ion. This is atomic mass 2 hydrogen ion. Fun fact, it's called deuterium. This happens in the sun. This is where all the energy, or a lot of the energy from the sun comes from. This is the formation of this. All right, let's do another one. Let's do carbon. Draw that. The last thing we do. It's time to go after this. What did I leave out and why did I leave it out? I left out the atomic number. Why? Because I gave you a periodic table. So I want you to get used to looking at it, right? What's the atomic number here? 6. Good. Here's another. Like I said, there's all kinds of ways you can do this. You could draw a million pluses and ns and all that kind of stuff. Or you could just say protons equals 6, neutrons equals, how many for this one? 6. And I could walk over here and I could go, okay, protons equal how many? 6 and neutrons equal 8. Good. So far so good. Okay, and then I put my electrons, right? And how many electrons do I have in the second shell? 4. What did they discover in that gold foil experiment? Nucleus. Good. What did they discover in the oil drop experiment? Charge and mass of an electron. All right. God bless you. I'll see you next week. Like it. Am I the kid or she the kid? See the kid. Do you know who he's talking? Yeah, I mean, you want to take a seat? It's going to take a second. I got to get my head into it.
You're good, no worries.
I'm not going to check your final answer. I'm just going to check your yourself.
this is pretty much right. So
Yes.
Friday again.
Yeah, everyone is great.
Okay.
Yeah, you do.
Thank you.
Well,
Proud of you.
I said about they said I did